The next choice of test in the application of the oscilloscope is one I actually have a great deal of pride about, and it focuses on two really important things: speed, accuracy, and simplicity. And I'm not aware of anyone having actually applied this technique of testing common rail prior to us about 15 years ago. It's about using the oscilloscope to very accurately test what could be a fairly complex arrangement of hydraulic and mechanical events, which essentially sums up common rail. The objective is to prove the performance of the high pressure pump under full load, and not just to prove its pressure, but with hydraulics, it's not just important you reach a certain pressure, it's the rise time, how quickly it takes to get to a set point. That proves hydraulic efficiency and flow, and also what we call decay, the ability of a system to withhold or contain or store pressure, which also is a critical function of common rail. Now, decay can be progressive on some systems, therefore we can predict leakage, and they're all incredibly predictable, event against time. In our case, this particular variant uses piezo injectors, and with this system, which is a Bosch-based EDC17 control system, there should be no decay once this test has been concluded. So once again, whilst maintaining speed and accuracy, we're able to prove conclusively that there is no system leakage. So what components are we actually testing? Well, the pump builds up pressure. The pump shouldn't leak because the pump is part of the pressure containment circuit. The rail is definitely part of the containment circuit, and so are the injectors. And quite often there may well be a mechanical limit valve in the rail, also controlling the containment of pressure on some systems. In our case there is not, but there is a device called a DRV, which when fully closed is a containment component, and we're going to close it. Basically, we're going to take control of this away from the ECU. In order that we can achieve that, I have unplugged the volume control device, which is a fail open device. Both of these devices are ground on control. If I unplug that, it's fail open, maximum flow, maximum pressure. I can then take control of the DRV, which if I then take manual control and provide a manual ground, that device will be driven closed, and the pressure built up in the system by the pump cannot escape. So basically what we actually achieve is a maximum proof test of that pump. And that enables us to prove many, many things. The efficiency of the low pressure priming pump, the flow characteristics of that pump, whether the filtration is blocked or not, because all these have an effect on rise time. The efficiency of the pump, the rotation speed of the pump. And that, of course, that word rotation speed takes me back to cranking analysis performance, because we could also conduct this test under cranking conditions where rotation speed from the starter motor is also a critical factor in building up pressure in the right period of time, rise time. And it also proves that the containment system, the DRV, the pump, the accumulator, the rail and the injectors are all holding pressure correctly. All with clean hands and all within a matter of seconds of conducting this test. So quite proud that we established this, I think around 15 years ago. That's what we're going to do. So we're looking at the importance of sample rate to gather this accuracy of information of very high pressure from the pump, high sample rate, extended base time. So we've got a very high sample rate, 4 megasamples a second across the sweep time. The sweep time is 50 seconds, an awful long time. But given the high sample rate and the type of component, we get the profile. So actually see what shape the pressure has achieved. And of course, the information we're relying on comes from the rail pressure sensor itself. And we're relying on the data from that to enable us, which is a voltage change, and that voltage will be displayed on the screen as an indication of pressure. And we're going to consider filtering. I'm not a fan of filtering. Accuracy, speed, efficiency. I don't like filtering by nature. I do occasionally use it. In order to avoid filtering, I've chosen the main input channel, A, blue, from the rail pressure sensor to have a floating measurement. I am not using a generic ground. The ground is coming from the sensor itself and the signal is coming from the sensor. Therefore, eliminating the rest of the car. The rest of the car does not exist so far as channel 1 is concerned, because its only reference, potential difference, is across the sensor, and that removes an incredible amount of noise interference. Word of advice, if you're not sure of the ground reference, you must first establish the accuracy of that ground with reference to battery negative, which in our case actually in the boot, but nonetheless you must do a voltage drop test if you have to, from the battery to the body, from the body to the circuit. Once you've established what that reference is, you can then rely on the value of that ground. So let's begin by conducting the test. So I need to run the engine. We can establish initially profile. So what I'm going to do first of all is turn the ignition on, start the engine, run the engine at idle, operate the throttle. That will not give me full system pressure, but you'll see a rise in pressure. I'm then going to turn the key off, and then we're going to look at that profile. That's the first thing I'm going to examine. So everything is prepared, we're all connected, and we're ready to go. We're all ready to go. First, I need to change the time base. The time base we've got here is too short. I want 50 seconds. We're looking at the control duty cycle to the DRV, it's an actuator based on nominal battery voltage. I'm not interested in current at the moment on that device. In fact, it's just powered down. But more of which side of that device is being driven, because it's ground on, I want to take control of it. I want to look at an event over 50 seconds. So the time base wants to be 5 seconds per division. I am not interested in the control of the DRV, so I'm actually going to turn channel B off. We're concentrating on channel A only, free run, no triggers, no filtering, and we're now ready to start the vehicle and conduct the test. As you can see from those results, we have a profile. And from this profile, we can establish the hydraulic efficiency of this system. I've done a number of tests there. I've turned the ignition on, started the engine. So we're going to look at rise time, initial rise time. The system operating pressure at idle on this system is around 260 bar of pressure, represented from the rail pressure sensor. Should equate to about 1 volt. So I expect to see around 1 volt there if that pressure is being maintained. I'm limited to the amount of how much throttle I can operate on this vehicle because it's an automatic. So you only get a partial rise time at increased pressure. I then allow the pressure to return back to idle. I then switch off and then started promptly again after switching off just to see if the rise time was any different once the system effectively had been primed, and then switch off again. So that's the profile. Let's now have a look in some detail at the performance hydraulically of this system. So I want to focus on, that's the tool I want, to go back to the main frame, that's the tool I want. So let's have a look here. Now, first of all, you can see it's a 3-piston pump driven essentially by the cam belt. We can see here that we start the threshold or plausibility voltage, if you like, on this system is 0.5 volt, as with all Bosch systems. So I expect to see 0.5 volt value out of the sensor with a static pump, and we have 505 millivolts. So I'm quite happy with that. Does it prove accuracy through the entire range? Not necessarily, no, but it gives me confidence. Output, power, ground, all are present, and the predicted range appears right. We then have to build up a certain pressure, represented by voltage, before the injectors are released. So we can measure, let's take a broader view of that test. We can measure rise time with the vertical cursor. So I'm going to pick a point there where the pump begins to rotate, and a point where the pressure maximum peak value was reached, which was there. And on this particular system, 0.3, 0.5, 300 milliseconds, 500 milliseconds would be acceptable. And we've reached that point in 549 milliseconds. So I'm fairly happy with that rise time. We're going to challenge that much more aggressively a little later on when we come to the proof test. So happy with the rise time. Does it conform with the values that we're familiar with? Yes, it does. We've done a lot of research over the years on different pump systems, and you know what? A given pump type will produce an exact rise time and an exact decay time. What's the pressure at idle? Well, we can measure the average voltage across, and we have 1.066. Absolutely on the money. 260 bar, 265 bar. I don't need to check it any other way. I know the pressure's there. Does that prove everything's okay? Well, you know what? No, it doesn't. Because the actual duty cycle of the DRV, something we're not focused on at this particular point in time, but the actual duty cycle of the DRV must also be correct. Therefore, the control matches the performance of the event. Very, very important. At the moment, we're just focusing on the testing of the pump, not of the control system. As I say, it's important you know the duty control cycle as well as the net result. In other words, if we had a leak, we may well attain the right pressure, 1 volt, but the duty may have to be increased to achieve it, in which case, prediction of leak. We don't know where the leak is, but it's accurate prediction. Accuracy, speed, efficiency. Happy with the rise time? Let's have a look at the next section. This is increased load, not maximum load, but certainly increase in load. So I'm not going to measure rise time, it's not appropriate. We're going to do a proof test shortly. But I am interested to have a look at how it builds up pressure. What I don't want to see, and sometimes when there are faults, what you may see is a rise in pressure with a corresponding drop in pressure, suggesting there's a leak or a weakness or tightness somewhere in the system. I want to see a progressive rise within a certain period of time. This happens to be normal for this pump. The characteristics of that image are correct. And I guess by having made that statement, what I'm actually implying there is experience. And yes, a lot of the interpretation using a scope does come down to knowledge of the component, its functionality, and experience of the image that you're measuring. Very important fact of using a scope is that when you measure something, you must know what the expectation is against the operating conditions. I've used those two phrases very carefully. Let's have another look at this little section here. This is the rise time again on restart, engine off, restart. Let's have another quick measurement of that rise time to see if it's differed at all. So there we have a very clear indication when the pump started to rotate. Again, so I'm going to take that peak there, and that is 345. So I did say about 300 to 500 milliseconds. It's down to 345 milliseconds to go from 0 to 260 bar. That's pretty efficient. Quite happy with that. Now, regrettably, with this particular system, when it comes to switching off, we can't measure decay in the rail. A, there shouldn't be any, and B, because of the way the systems operates, they deliberately dump any residual pressure by opening the DRV, or at least allowing no current to flow through the DRV. And that's for safety, so that on the next restart, the timing belt is not having to drive a static hydraulic pump with a lot of pressure in it. So we have to work out the decay some of the means. So profile, I'm happy with. No problems with that at all, but it doesn't challenge the pump enough. So what we're going to do now is run scope. We can, we'll keep the cursors where they are. We may use those again. I now need to set the throttle at 2000 RPM. Why 2000? Because the test I'm about to conduct is actually to short to ground the DRV, so ground on device. I become the control. By shorting the DRV to ground, that DRV is hammered closed. There should be no ability for diesel fuel to escape the system, unless there's a problem. And I want to keep it held to ground to prove that there is no decay, because on this system, once the injectors are discharged, because these are piezo injectors, I'm not going to use the word off, once they're discharged and closed, there is no means of escape. So we're proving the integrity of the high pressure system. When I do that, the ECU is going to drop the hammer suddenly and kill those injectors, because the way the ECU software has been written is to protect the engine against potential hydraulic damage. When it sees vast differentials of pressure control, it will drop the hammer on the injectors. Basically, it will discharge them instantly, preventing the engine from running. So the 2000 RPM rotation speed is to allow, even though the injectors have been terminated, to allow rotation to continue on the pump to maintain the pressure in the system until the engine speed naturally decays. So let's start the engine, set the throttle at 2K, and we'll do a proof test. First thing, we'll get the engine running. Reset the time base. It's good ground. You see how quickly the ECU terminates the operation of the injectors. I'm holding it still to ground. Maximum current flow through the DRV. You will not damage it. And I'm just monitoring. You can see the pressure is up at 4.5 volts. I'm still holding it, and if you listen carefully, when I release this, you'll hear you've 1650 bar, about 25,000 psi in that rail, and that sudden is the release of pressure from the system. Now we can have a look at the data. We've gone to the second frame. Let's go back one frame. Just move that. So, engine running at 2000 RPM. So we'll have, well, we've got about 1.8 volts. We'll probably have about 450, maybe 500 bar pressure in the system at that point. I then take control of the DRV. Now this is the critical. This is without doubt the most accurate test of a high pressure pump, even more accurate than any test bench that pump will ever be supplied to. A, because I've not taken the pump off. I've not wasted the labour in doing so. I'm testing under real conditions in real time, and the accuracy of this measurement will match any test bench anywhere in the world in terms of individual performance of the compression chambers. Now let's just expand into this one more time. Now look at the accuracy there. Each compression event is being seen. So if there was a drop in pressure from anywhere, we would see a greater negative deviation. The contribution of each of the pumping elements or events is progressive. And you can see that when I maintain a closed DRV, the engine by now has cut. You can see that we've made, let's measure it, should be 4.5 volts. Pull that down, it is 4.618. Now all sensors, remember the ranges, 5 volts, 20 volts, 200 volts. 3 ranges. We're dealing with 0 to 5 volts. All sensors operate in a range of 0.5 to 4.5. So at 4.5 volts, this system has maintained maximum pressure. Now the system is a 1650 bar system. For all I know, there could be 2000 bar in that rail. All I can tell you is it's 4.5 volts. So it's made its maximum pressure. And it's contained it, which is the important part. So we need to look at rise time. Now I did say that the rise time of this system, 0.3 to 0.5, but however we're now at the higher speed, so I expect this now to be much quicker, below 200 milliseconds. So this is now the rise time on full load at 2K. 2K is a standard test parameter, and the rise time there is 1.87.1 milliseconds. Absolutely on the money. So I now know that this pump is totally hydraulically efficient at maximum work rate in situ. So I have proven priming, flow, filtration, operation of the pump hydraulically, and the maintenance of pressure in the system for integrity or tightness as it's sometimes called. And if we go back just one more level, you can see, I'm going to use the word semi-indefinitely. That pressure would have been maintained semi-indefinitely in the system, proving 100% that there is no leakage across those piezo injectors from the spill circuit, which in the case of Bosch is how they should operate. So all of those tests took less than 5 minutes, in fact even quicker than that, and I now know entirely the hydraulic functionality of this common rail system. Very effective test, and one we're very proud of, that we've developed over many years, has now been used very successfully by a lot of people out there and people who've been on our training. So that is one of the purest examples of the application of a scope to measure a mechanical hydraulic component. Very focused. I think that points out the importance of accuracy, application, and success and profit, of course. So that is the proof test on common rail.